By the way, now you can. So yeah, I'm gonna start my lectures about super topological recursion. And before even talking about my plan, I wanna first explain what this super means, because I don't think this is a common subject that you study in graduate school. So Z2, okay, sorry, I already spoiled something. So the definition, so so the reason why I'm saying this is when somebody says super, it actually means a lot of things. Sometimes they mean a supersymmetric theory. Sometimes they just mean some sort of Z2 grading. And then I want to make it as clear as possible what I mean by super in the first part of this talk. And I try to focus on more like conceptual part, and the computational things are always in the exercise so that, I can skip many things. All right, so I'm gonna first set out a bunch of definitions / notations. So for some reason, okay, so I'm gonna have a bunch of stuff, so I'm not gonna write definition every single time. A super vector space is just a Z2 graded vector space. That's it. Okay. So it has nothing to do with anti-symmetric blah 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 at the moment. It's just a Z2 graded vector space, meaning that so V is now V, say 0 plus. This is the common notation. And now notation, any elements in V0, okay, first of all, yeah, the order is kind of important to make everything clear. Okay, good. So any elements in V0, we call it even. Okay, just a name. Any element is called even, and any element in V1, this is odd. Just a name. Instead of saying like 0 and 1, we just say even and odd. And okay. And then element in V is called homogeneous. If V is either this or this. So if, of course, in principle, you can have some element which is mixed, which has both even and odd part, but for most of the time, we actually care about the homogeneous element. And okay, so now we need some sort of, so now they're called parity. This is basically a map, strictly speaking, to Z. Actually, more strictly speaking, it's just 0 and 1. And then this parity, then we denote by this, like the norm sign for some reason. And then this to be defined to be 0 if V is, how do you call it? Even? Yeah, good, I thought this lecture is supposed to be like more like interactive, okay? And V is 1 if V is odd. Okay. By the way, sorry, I don't have anything here, so I have to like keep walking back. And then I didn't have iPad from Japan. All right, so the last thing, let's say the dimension of V0 is say D0, and dimension of V1 is D1. And then we just denote dimension, in this case, we denote dimension of V as D0 slash D1. And this slash notation appears everywhere. And I'm sorry, but sometimes the slash means how many bosonic elements you have. Also, okay, it's also important. So this might be called bosonic as well. Okay. And odd one, sometimes called fermionic. And in my lecture notes, I try to be as consistent as possible by using even, odd. but when I speak, I can't guarantee anything. So this is just a dictionary. Whenever I say bosonic, you should think that there's some sort of element in V0. All right, so then now, of course, we can think about some sort of maps between two vector spaces, and then that also admits similar notation, meaning that, okay, suppose now you have some map.
If it's not homogeneous, then you can assign parity.
Correct. Yeah, the parity is designed only for the homogeneous element.
So the parity doesn't go from V, but
Sorry, yeah, yes, that's yeah, okay. Sorry, yeah, so the parity is defined only for homogeneous elements. Thank you. Yeah, so then the notation basically goes through to any map. So suppose you think, okay, so now V, let's say V and U are both super vector space. And then, of course, in general, you can think about any random map between two vector spaces. But you can, in particular, think about parity preserving and parity reversing morphisms. And that means, so phi is said to be parity preserving. Okay. Okay, I should have done whenever I even, bosonic, homogeneous, fermionic, odd, parity, good. And parity preserving if suffice, and in particular, yeah, what is the best way to say? Maybe this is the best way to say. This is in, you know what? This is not what I want to say. This is in V, which one I think? UI if parity of V is I. Am I correct? I think it is. And then, of course, now you can have reversing. By the way, I might have typos on the board, and please point out, again, it's supposed to be interactive. Parity reversing if it's the other. So far. If I was gonna put mod 2, but yes. So far so good, I guess. Any questions so far? I guess no. It's just a notation, right? Nothing crazy. Okay, so now I wanna give some sort of product structure, like multiplication structure in this vector space. So basically, I wanna define some sort of algebra. Super algebra is a super vector space together with some multiplication rule. Together. Multiplication, sorry, super algebra A, and sorry, is together with here, it's important, parity preserving. Sorry, is that correct? I think it is. Is parity preserving multiplication? Yes. Parity preserving multiplication. Parity preserve. This means that for all homogeneous element A and B in A, so they are homogeneous. A dot B of the parity of this guy should be A plus B. This is what I mean by parity preserving. I guess it makes sense. So if you multiply even and even, you get 0 plus 0, which is 0. Even and odd, 0 plus 1, so it's going to be odd. And odd, it's 1 plus 1, it's... Okay, sorry, I should have said maybe mod 2, but 2 is 0 if you mod by 2. So that's going to be bosonic again. All right, good. So, okay, so far no anti-symmetry going on, and I think if you have seen super or supersymmetry in literature, I'm pretty sure you found some type, like, okay, some sign and blah, blah, blah floating around. And so in principle, superalgebra normally means just this, so just Z-graded algebra with parity preserving. But in practice, many people actually means little more than that. And this is, for example, maybe the first instance that you see like this actual meaning of super is so-called supercommutative algebra. Now definition, so not just superalgebra, but supercommutative algebra. Sorry, A is said to be, I think that's a better way of writing. I'm so sorry if you're taking notes on the paper note. If it's iPad, it doesn't matter. A superalgebra is said to be supercommutative if for all homogeneous element in A, homogeneous element A, A times B is now B times A. Okay. So this is what I mean by supercommutative. So this is more like additional constraint, or additional condition that I would call any algebra having this type of anti-symmetric relation, I would call it superalgebra. Sorry, supercommutative algebra. Does it make sense? So, okay, so now let's do some exercise. If it's bosonic and fermionic, what is the sign? Plus or minus? Okay, it's plus, okay? Yeah. If it's, because sometimes people get confused. If it's bosonic and fermionic, because parity is different, you might think, you know, they, sorry, yeah, good. All right, so now let me give an example. Is that clear, by the way? Is that a question or just confusion, or good? Okay, so I would assume if Danilo, Ranier, and Ale didn't ask, that means it's okay. Okay. All right, so let me give an example of this supercommutative algebra. So now let's example. Okay, starting with the super vector space. Now I can introduce coordinates. Let's say, okay, so suppose this is super vector space. And then I introduce coordinates, say Ti and tau I. Is it legible? Is it distinguishable? Yeah, and it's big enough because. Yeah, okay, that's what I actually did in all my lecture notes. Good. Exactly J, I think. On the lecture notes, T and tau are quite different, but you know, on the board maybe not. Where so I basically goes from 1 to D0 and J D1. Okay, and then to construct, so okay, so basically now I want to construct, basically I want to think about the algebra to be, I want to say, this is what I want. I want to have basically polynomial ring of these guys. And I want to say that this is in fact a supercommutative algebra. To do that, I would kind of impose some condition on these odd coordinates. So they're so they're coordinates for V0, and tau j's are coordinates of V1, odd coordinates. And I would impose that they actually are anti-commutative, meaning that tau I times tau j, the coordinate, and they're actually called Grassmann variables or Grassmann numbers or Grassmann parameter, whatever that is. This actually anti-commute. J. Okay, maybe I shouldn't use I and J, right? I guess you understand what maybe J1 and J2. That's better. J1, J2. Yeah, you know, because if you're learning, it's probably better to make it everything clear. No. Are you okay with that? I just introduced these formal variables following this rule. And then if you have never seen this before, tell me what this is. Suppose this tau j follows this rule. What is tau j square? It's 0, okay? Okay, so it's, if you have never seen this before, it's a little weird object, but they are going to be kind of useful. And then if you accept these coordinates, and then this guy is in fact an example of supercommutative algebra. Good? When did I start? Okay, good. Whew. All right, so now, but I really need to do this, otherwise I'm pretty sure everyone will be lost, except a few people who are familiar with notations. So now I'm going to define basically the Leibniz rule. Okay, so so now the definition again. A super vector space, super algebra maybe, strictly speaking. And consider D in endomorphism. And then D is called derivative if, so basically I'm defining the Leibniz rule on the endomorphism A. So then D is, well, strictly speaking, single derivative, but if for homogeneous again, for most of the cases when I write this, it means they're both homogeneous. But I kept writing somewhere like here and there, but I may drop that just without conscious. For homogeneous element N and B, D of A, B is B plus minus 1 to the parity of D and parity of A and D of B. Does it make sense? So it's what? This is the parity. Remember that? Yeah, so it's, I'm going to give you an example that will probably make it much clearer. Okay, so this is just a definition of basically Leibniz rule. Whatever satisfies this condition is called a derivative. An example. Yeah. Sorry, what? Which part are you talking about? D is what? Yes. Sorry, that was the question. Sorry, yeah, right. So D is because it's any morphism because you're actually going to have both parity preserving and parity reversing derivative, and then that's what I say. Like maybe after giving example, it's going to be clear. So example, okay, let's now use these coordinates to make everything concretely clear. Then of course, as you can imagine, in that coordinates, this d by t, this is a derivative, as you can easily imagine, I hope. And this one is also a derivative. Okay, let's say A is in fact this guy. And then now I can think about the derivative. Okay, example, let's take A. Sorry, A is the same as any typo? This? It's D.
Okay. So you haven't written it, but the parity of morphism is 0 considering one of its recursive.
Yes. Sorry. Yeah. Sorry. Yeah. What? Yeah, okay, sorry, yeah, that's also true. Okay, yeah, sorry. Yeah, so the parity of morphism itself is also called, sorry, the parity of morphism is 0 if it's parity preserving.
Sorry. But by definition, it has to be either parity preserving or parity
Yes, yeah, right. So, sorry, so, okay, so as I said at the beginning, for most of the cases, unless I specify it, I'm always talking about homogeneous elements. Okay, maybe I should, okay, so, fine, clear? Sorry, yeah, so, if it's parity preserving, the parity of phi itself is 0. This means that phi is 0, and this is phi equals 1. And then, unless I specify, I'm always talking about homogeneous elements. Okay. Yeah, thank you for pointing that out, because yes, yeah. As I said, I sometimes even drop even this homogeneous. Or should I keep writing it? Okay. Okay, I'll try to do it as much as possible. But if I forget, just because once you're used to it, you don't even think, and then it's just automatic. But I know that this is a school, and then it's definitely a fair question. So please.
In that case, you should also write it.
So what?
D is also
D?
first line. D is homogeneous element at A. We can just assume that everything will be always homogeneous and then we will.
Yeah, right. So unless I specify it's going to be homogeneous, is that also fine? Then are you all satisfied and convinced that they are all derivatives? And in particular, the parity of d by dti is parity of this derivative operator. This is 0. And then the parity of, so this is odd coordinates. Okay. And this, I define this to be 1. And then, actually, in fact, in the exercise, probably the first question in the exercise, you would be asked, if you assume this, the parity of this guy to be 0, there will be some contradiction. So it has to be -1. Or in other words, this has the sign, it has to pick up the sign if depend on the parity. So that's going to be an exercise. Any questions? And we have just one more definition before jumping into the main contents of this lecture. So the last thing I wanna just mention is a Lie algebra, but super version. So now definitions. This is possibly the last annoying definition you will see, modulo a few more. Super Lie algebra. Sometimes people denote Lie super algebra because you define a super algebra, then you're putting this Lie bracket. But I like this name better than Lie super algebra, but it's just up to you. It's a super algebra. It's fair because now I say literally a super algebra, so maybe it should be Lie super algebra. Super algebra whose multiplication operator satisfies the following condition. So it's basically satisfies the condition you can imagine with some parity conditions. Okay, I didn't forget A, B, C, all homogeneous elements. So the first condition 1, A and B. Okay, maybe to make it crystal clear, let's put sub S here. So it's a super Lie algebra operator, Lie bracket. So the super Lie, super Lie bracket satisfies these conditions. And this, is that correct? I think it is. Does that make sense? So if you just work on just Lie algebra, this picks up the sign. It's a skew symmetric, right? It picks up a sign. Now, for the super Lie bracket, it picks up a sign up to this parity contribution. And 2, now we have super Jacobi identity. This is almost impossible to remember. But I think this, okay. So now the super Jacobi identity is going to be C, A, B, and C plus reasonable permutation of ABC. A, C, A, oh, no, sorry. Sign is always important. I'm so sorry. Does it make sense? Okay, the sign, okay, there might be some, I'm pretty sure this doesn't have a typo, but as long as you understand the concept, I'm actually happy, because in school, you don't care about the detail too much during the lecture at least, and then if you care about the detail, just do exercise. Yeah, so I guess it's clear. Yeah, it's just a binary. Yeah. But I mean, we have Jacobi identity. But all right. So now what? Okay. So let me give you an example. So now let's take this example. Remember, we had polynomial ring of Ti, even variables and odd variables, and we declared that they are derivative operator. And then now, example of super Lie algebra is that if you think about something like this, so now say D of A is that guy. Okay, this A. Maybe I put some tilde, specifically meaning that A, not just random super algebra. If you define this as span of, something like this, so just one derivative, and you have any element in A in front of this guy, then, sorry, what? Yeah, all of them. Yeah. And then, wait, now what? And then if you think about this guy, wait, you ask for all I and J, right? Is that what you're saying? Ah! Okay, maybe I shouldn't have done it. Right, and then, so now, and then in particular, now you can actually have this Lie bracket as expressed as possible. So if you define this, D2 in, again, they are homogeneous elements. Okay, good, I didn't forget. Homogeneous. And then this can be defined as something like this, D1 acting on D2 minus parity of D1 and D2 of the other one. I think it's reasonable, right? I hope. All right, sorry, I cheated. So this is absolutely the last definition in part 1 of lecture 1. So now, so we define the derivative, and we want to define integral as well. And then integral is little, possibly even counterintuitive for you, but the integral sign this is defined, say, okay, so now of course you have this kind of the determinant thingy. So let tau be an odd variable. Then the integral, this is defined to be 0 formally. And then d tau, this is defined to be 1. This is the definition of this sign. Okay, you have to live with it. But if you accept this definition, and it actually works well, then you will find that, in fact, this operation is exactly the same, in practice at least, as the derivative. And so this is a little funny, but this is more like the property of odd variable. And then also, there's no integral domain whatsoever when you think about integrals of odd variables. And this is also right. So you actually can really think of this tau as formal object for most of the time. Okay. Good. So now we've gone through all kind of mathematical definition, and also more like we fix the convention of what we mean by super. So the super means Z-graded thing, but for most of the occasion, we actually introduce those sign conventions, and that's going to be important for us. All right. So any questions so far? Good. All right. So now I want to talk about supersymmetric algebra, which is a particular example or a particular class of examples of super Lie algebra. Okay, so now I'm not going to, by the way, define a supersymmetric algebra because it's actually going to be hell. So more like a comment, supersymmetry algebra is a special class of class. I don't know if class is a good word, to be honest. Type, maybe? I don't know. You know, I'm not a native speaker. Of the super algebra. Did I say super algebra? Algebras. And in particular, actually, it has a name. Another way of saying supersymmetry algebra, this actually admits another name. It's called super Poincare. I'm not sure if it has dot algebra. Sorry, what? No, supersymmetric algebra really means that it's actually super Poincare algebra. Because this. Okay, but it's so given the super Poincare algebra, which is given the Poincare algebra, which is just isometry group of so this one is isometry group of right? Okay, so now given this, and now you can basically think about little difference on this slash notation. Sure. All right, so now you have to think about what kind of supersymmetric algebra you can think of from this guy. Right? And then actually, the extension is not unique. So you can have many super Poincare algebras from a specific one. Is that your question? Or you actually think that there's another supersymmetric algebra that is not?
Yeah. Because it's not a unique extension.
Okay. Yeah. Yeah, but this basically tells you that the supersymmetry algebra actually has some sort of geometric role as well. And that's why supersymmetry algebra is more interesting than other super algebra. This gives some sort of geometric meaning as well. And this is also why physicists care about that. And the physicists normally care about, in particular, physicists normally care about so-called unitary representation of supersymmetry algebra. Of course, we are not going to talk about that. It's too much work. But I think what you have to keep in mind is supersymmetric theory is heavily constrained. Because we have more symmetry, we want to have some theory that respects those symmetry. It means your theory is heavily constrained. And quite often, physical theory can become topological, or at least very simple, and importantly, it sometimes can become mathematically definable. And this is very important. And for example, an instance of mathematically definable physics is so-called n equal to, at least pure, not necessarily pure, whatever you see this sentence, Seiberg-Witten theory. Okay, maybe not Seiberg-Witten, Super-Yammel's theory. In 4 dimensions. This sometimes is called class S theory. Sometimes Seiberg-Witten theory. This, I think if you are a physicist, this speaks a lot. But if you're a mathematician, it's like a black box, right? But you can actually define the partition function of this physical theory as basically the generating function of the volume of some moduli spaces. Okay, so now the moduli spaces can be well defined for some, whatever the pure means. And so now you can ask a mathematical question. What are they computing? Are they counting some nice objects? And that's why supersymmetry is nice. At least that's one aspect why supersymmetry is nice. And then there are many other instances. For example, if you have, you know what, there are many other good examples. Some of them actually can be thought of as a toy model of mirror symmetry. And that's called n equal 2, 2 nonlinear sigma model. I think you've heard of it. And if you do the so-called topological twisting, you can have basically some sort of homological theory. And that is also somewhat, you can define it mathematically. But for this lecture, we will focus only on 3 particular supersymmetry algebra. One of them, the first example, so we basically, instead of giving a definition, example 1, so it's basically 1/1 supersymmetry algebra. Meaning that you have one even element here and one odd element here. Okay, should I give a name? A of 1/1 maybe? I don't know if this is a good notation, but I just invented it right now. So this has one odd generator, Q, and one even one, D maybe, such that they satisfy this anti-commutator relation. Okay, this is just an algebra. Now I'm going to give you some nice representation of this guy. So let's take, again, the coordinate. Yeah. Good. So this. All right, so this, thank you. This bracket means, okay, in general, this means one. That's right, because I put bracket S. This is just anti-commutator operator. And then for this case, we have only one generator, so we actually have only one Q. And this satisfies basically 2Q square is, sorry, I said that QQ is 2D. QQ is 2D. This is the equivalent of saying that Q square is D square. Oh, sorry, D. Am I too fast? I guess it's fine. All right, so now let's make it more concrete. Like, okay, so now let's prepare one even coordinate or variable and one odd variable. And now, and remember, like, the supersymmetry algebra always has some geometric meaning. So I want to basically think of some sort of meaning in this algebra. So let's say D is just a derivative operator, like the simplest possible derivative operator you can think of. Now Q. Can you guess? Okay, so it's okay. I'm going to declare this is going to be a derivative, and from which you can, I guess, imagine Q should be odd, right? Anti-commutator odd and times odd is going to be even, and this is an even operator, and this is going to be a derivative operator. So you can imagine probably it's going to be something like this, right? But if it was like this, what is this? Can you guess? It's 0, because if you have exactly the same element twice, it's kind of the same analogy as this is going to be 0. So this one should also be 0 if you make it square. So you need something else here, and then the something else is going to be tau and d by dt. This is the answer. So this is the simplest supersymmetry algebra we can think of. And then, because this school is about topological recursion, I want to already give some sort of meaning or some sort of, I don't know, sign why we have to be a little careful about ramification points. All right, so I just said this is a supersymmetric algebra with this commutation, anti-commutator relation, right? But I can have another. So okay, so suppose I prepare the same coordinates. Now I define this the tilde by saying that T and then Q tilde T tau d by dt. Okay? And then you can do a straightforward exercise. This also implies the Q tilde being twice of D tilde. So this is also an honest some sort of representation of this algebra. So why do you think I mentioned about this? What is where the problem possibly appears? Can you tell? So if T is 0, this operator will be degenerate. And we kind of don't like it. So now what we can do, so okay, just for whatever the reason is, let me introduce another coordinate, say S square is T. Okay, so I do this 2-to-1 coordinate transformation, basically. And then you can actually write this D in terms of S. In terms of S is actually d by ds, maybe half. And Q tilde is going to be and it goes back to this, the standard, most standard case. And then now you see that, so basically what I'm saying is that if you write something like this, it has a degenerate. So this operator is degenerate when T is 0. But if I write in terms of squared coordinate, it's going to be nice. And then you may or may not wonder, this looks pretty similar to the Airy equation. And T goes 0 or S goes to 0, in fact, corresponds to the ramification point of this curve. So I don't think I have time today for this lecture, or maybe not even tomorrow, but if you want to think about some sort of geometry with supersymmetry, you have to be really careful at the ramification point. And this already suggests, of course not, I'm not talking about geometry at all, but this already suggests that you have to be careful at ramification points. And this is where some geometry becomes actually interesting if you want to rewrite super topological recursion from geometric point of view.
D tilde S related to D tilde?
D tilde S?
D tilde subscript S.
Yeah. D tilde. Oh, so no, they're the same thing in T coordinate or S coordinate. If you do this 2-to-1 map, you just plug this in. Okay, could be the other way around. Is it the other way around? Okay, I can't remember, but I think this is right. So basically, okay, yeah, how do I start? No, it shouldn't be T squared, then it's probably the other way around. Exercise, maybe. Okay, find out typo. Okay, find out typo on this board, but it should be one of the other. So yeah, okay, now I feel like this is wrong, in fact, so maybe this should be the other one. Thank you.
Then the other one is going to be
No, I know one of them works, but
that.
wait, is that what I want? No, I don't think so. No, I know this is what I want, but I can't tell. Yeah, exercise, I guess. Sorry about that.
I think both of those will not be. S equals T squared and S squared equals C.
No, okay, so it's T. Should I do this here on the board? Wait, so it's, wait, no, that. Is that right? Because no, if T is no, if T, okay, sorry. So if T is S square, so if T square is S, then what? T is, okay, ignoring about the sign, T is square root of S. So d by dt is now d by, so wait, so the T equals okay, yeah, right. Okay, sorry. Some transformation. Okay, so sorry about that, but some sort of ramification thing will appear. Okay, okay, forget about that embarrassing moment, and then now let's move on to supersymmetric version of SL2. That's going to be important for us. So now out of a sudden, let's so now the next example is so-called OSP1. 1/2, in fact. And then this will be generated by a bunch of, so it will be generated by 3 even generators, and they satisfies the SL2 commutation relation. So they basically actually forms the subalgebra in this OSP1-2. And so they're even, and you have 2 odd ones satisfying the following relation. For m n in either -1, 0, 1, L. Sorry, what? Okay, and then now R and S in either ±half, and then now anti-commutator of R and S equals twice of, is this what you're asking? And then the third, M is in one of those, and then R is in plus or minus. Then Ln GR is So you can think of this OSP1 to algebra. This is super algebra, super Lie algebra, whose generator satisfies this super commutation relation. Okay, because again, I'm not defining generally what supersymmetry algebra is, but this is an example of super Lie algebra and supersymmetric algebra. Okay, so and this is by the super generalization. This is a supersymmetric analog of SLT. Yeah.
M for greater, like L or something greater than 1, or is this just mod conditional? It's like an L, M plus N, a new object that's not on this.
Okay, so I think, is that right? You're asking if both of them are 1, and it sounds like you're going to get L2.
Yeah.
But if both of them are 1, actually going to be 0. So you actually don't get L. Yeah. And then the same thing for -1 too. If it's a minus and -1, get 0. Yeah. All right, but that's going to be actually a good question because that's going to lead to the example 3. So another way of reflecting that. Let me check the. Yes, thank you. Yeah, that's right. Yeah, it has to be this, right? Is that what you're asking?
Yes.
Good. Yeah, so that's definitely true. Yeah. All right, but now we've got a question: what happens if it's 1 and 1? In that case, it's fine. But then you can ask the question: what if we generalize this m and n to any integer, plus or minus? And you ask also questions. In that case, maybe it's also natural to extend r and s to be all half integer. But when I say half integer, it means integer plus half. And then that actually is possible with even so-called central extension. And that's going to be example 3. So take the same commutator relation, and now generalize m, n to. So now take the same commutation relation, and but now we allow n and m to be all integer, and r and s to be all half integer. Okay, and then this is again another example of supersymmetry algebra, and in fact it's even more. By the OSP1-2 is actually even more too. So this is now going to be, first of all, infinite dimensional Lie algebra, super Lie algebra, whose generator satisfies this commutation relation. Such an algebra is called super Virasoro algebra. Okay, super Witt algebra, strictly speaking. And then in this case, such an infinite dimensional super Lie algebra is called the Witt algebra, strictly speaking, in the so-called Nevius-Schwarz sector. Okay, and then furthermore, it turns out you can make a bit of extension by some central element. If you add, C is now a central element, which means it commutes with every single generators in this. It commutes with every single generators here, and I think it's m plus n 0, m cubed minus m, and then one more appears somewhere, plus C3. minus half 1/4. No, this should be wrong, but oh yes, of course this is wrong. Whew. It's here, and then sorry, square to be all right. So this is what I have in my lecture notes, and I'm pretty sure there must be something like this too, but I think this is so. But Wikipedia knows. Yeah, right. It should be this. All right. So and then once you central extend with this specific way, then such a superalgebra is called super-Virasoro algebra now. Okay, so if people say, if you think about Virasoro, if you see some word Virasoro or super-Virasoro, it means generator satisfies this commutation relation. And then with central extension, with that central extension, then now the resulting superalgebra is called super-Virasoro. And this is called super-Virasoro algebra in the NS sector. Okay, and this is also an example of supersymmetry algebra, and it is in fact an example of superconformal algebra. All right. I still have half an hour or something, a little more. Okay, good. So it's about an hour since I started. I'm Japanese. Exactly how I expected. All right, so now finally I can talk about the plan of my lecture. Okay, so I actually don't know what Bertrand said and what Nitin said in the part 1, but I hope they mentioned about the Virasoro constraint. Yeah, you did? Okay, good. All right, so now I'm gonna just draw a picture, a cartoon. So, okay, this formalism is so-called topological recursion. This is basically a machine that basically the initial data is, okay, maybe strictly speaking, spectral curve, which is a Riemann surface with a little more additional condition. And you plug this Riemann surface with some conditions into this black box, topological recursion, the residue formula, and if you want to do higher thing, you plug into the formula Ranier wrote down. And then this generates an infinite sequence of multi-differential, so-called omega GN. I think it's a good name. And then why this is nice? Because often if you choose this spectral curve in a very nice way, often they are going to be generating function of some nice geometric invariants, such as psi-class intersection numbers, Gromit-Tenno P1, and many examples. But, okay, so now suppose you want to think about the supersymmetric generalization of this formalism, because supersymmetric algebra is somewhat interesting. It has some geometric meaning as well as because it's an extension of Poincare algebra. But how do we do it? And okay, maybe idea is okay, but it seems difficult. Maybe you have to think about a super Riemann surface, presumably, and from which you can somehow get recursive formula that generates super multi-differential. That's a naive guess, but how do we actually do it in practice? And that's where we now think about Virasoro constraint. So Nitin's lecture and also Bertrand's lecture. Oh, maybe I'm not going to write it. It turns out that there's a dictionary between this omega GN that you can compute from topological recursion, but also the Virasoro constraint. So suppose you prepare a special set of Virasoro operators. Okay, you actually have to construct this in a very specific way, for example, as Ranier introduced this morning. Then if you prepare this with some, actually, so this one can also have some sort of initial conditions, which he will talk about in the afternoon. And then now I can think about some object that is annihilated by the Virasoro operators with the condition that n is -1 or greater. Okay, we don't want to think about it minus. So this is the highest vector of the module you can think of. Okay, so now because supersymmetry is even defined in terms of algebra, this seems much easier to generalize, even conceptually. So I guess now almost everyone in this room can imagine what I have to do to generalize this one into supersymmetric picture. So what we can do, so now we're going to think about supersymmetric generalization, meaning that now I prepare in a similar spirit, not just Virasoro operator, but the super partner that satisfies the super Virasoro commutation relation that I just erased here. Okay? And then what I would impose is, instead of just imposing this condition of, say, supersymmetric version, not just imposing this one, but in fact, why don't we impose this? Is it a fair conceptual jump? I hope. All right, so now because you can easily, at least relatively easier than this formalism, you can easily generalize Virasoro operators to super Virasoro operators. And then you ask the same question. Is there any object that is annihilated by not only the even Virasoro, but also the odd Virasoro part? And if you find one, can you find a corresponding geometric interpretation that computes basically this guy, but in terms of some geometric data? This is basically the goal. So then now the question is, can we, okay, first question, of course, can we find such object? And the answer is yes, and that is what I'm going to show in the rest of the talk and tomorrow. And if you find that, then the question, can we construct a dual geometric description of this super Virasoro constraint? Yeah. Because that's a good question. So, okay, yeah, how should I answer that? Okay, why I'm calling it supersymmetric? Because my generators are supersymmetric extension of Virasoro. Okay, so, and that's actually a very good question. So when when not only me, but when people say super, you actually have to understand what they mean by super. And what I mean by super is that the Virasoro constraints are now super generalized. Okay, but this doesn't mean that I now start with Riemann surface, I generalize to super Riemann surface. Suppose you find some recursion, do they correspond? That is not necessarily yes, okay? Because what I'm doing is I'm basically generalizing super algebra, super Virasoro algebra to, Virasoro algebra to super Virasoro algebra. Here you can do Riemann surface to super Riemann surface. Do they agree? That's another question. Okay. Then my approach is, or basically what you will study today is, we take this path. So that can we construct such that this is precisely, basically it's a dual geometric description of that guy. That's what I mean by super. Did I answer your question? Sorry, what? Mm-hmm. Okay, sorry, yeah, but that's okay, no, okay. That was your question. Sorry, no, but yeah, but okay, sorry, I didn't understand your question. Okay, yeah, right. So okay, yeah, what is, yeah, okay, sorry. But when I say that, it means dimension 3 or higher. Okay, good. Oh, sorry. Oh, okay, yeah. So right. So okay, so we are talking about physics basically now, but so in two-dimensional physics, that's normally called conformal field theory, unless you put some weird stuff. And conformal field theories can be defined in any dimension, but when dimension is 2, something special happens. And if dimension is 3 or higher, the isometric group is finite, isometric algebra is finite, and then everything is nice. In dimension 2, it turns out the isometric group basically can be enlarged, as you said. So now you can think about conformal transformation, which is going to be this infinite dimensional algebra. And as you said, OSP12 is more like the global part or isometry of the two-dimensional object, but you can extend to the conformal case. And this is what I mean by super. So yes, sorry, yes. So okay, now I understood your question. Thank you. Yeah, two-dimensional is special. Yeah, sorry, yeah, okay. Yeah, okay, sorry, yeah. Right, and another, okay, so now I'm gonna basically construct this one in the next half an hour or something. But before moving on to that, I wanna give a caution, or like important remark. So, as I said at the beginning, if you think about some sort of supersymmetric physics, sometimes it becomes topological and mathematically definable. But as you know, for example, some supersymmetric string theory, or some of this type 2A string theory, compact from the Calabi-Yau3, blah, 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 some of them can be computed by the standard topological recursion, right? Not the supersymmetric one. And this is another point of why I said when somebody says super, you have to be careful. So some super theory of physics can be computed by the standard topological recursion. Okay, this happens, and we've already have many examples. So now if you think about the supersymmetric topological recursion in this sense, what can we compute in any other field? We don't know yet. Okay, this is an open question, so I welcome everyone to jump into this business if you have time during your postdoc PhD professorship. And then that's basically an open question. And I think I have another remark that I can't remember. Oh, another remark is that, okay, you might expect some sort of relation between supersymmetric version and non-supersymmetric version. This may or may not, like, the answer may or may not be yes. So an example is if you think so-called bosonic string theory, it requires that the target space, if you think about this some sort of like sigma model thing, so if you think about the maps from Riemann surface to a target space, if you do the bosonic string theory, the target must be dimension 26, no matter why, but it has to be 26. And then, but if you do so-called supersymmetric string theory, the target must be 10. That's probably more like what you are familiar with. So even if you just change bosonic theory to string theory, even the dimension of the target changes. Question, comment? And another example, if you do bosonic string theory, you have some other problems, like some unstable objects that you might have to do. But if you think about supersymmetric one, some problems disappear. And then you can think about 5 classification of string theory, type 2, type A, so type 1, type 2A to B, heterotic, and E8 cross E8, something like that. So now we're going to present some sort of supersymmetric version in this sense of matrix models and topological recursion. And a priori, there's no guarantee that this has some relation to this. Okay? So just keep that in mind. So supersymmetric generalization is not a deformation of your theory. Okay? So there's not like supersymmetric parameter that if you set that to 0, you get the standard thing. It's not like that. Okay? So that's an important remark. Any other question, comment? Yeah. All right. So now finally, in the next half an hour, I'm gonna talk about a concrete example of this guy. Okay. All right, so now finally, section 1. Okay, I have a question for you actually. Have matrix models been mentioned in, yeah? And was it defined? I guess, okay. Yeah, okay, so the plan is, okay, so let's think about so-called, okay, now, what I want to say, okay, all right, so now let's think about so-called n times n plus n, one Hermitian matrix model. So today, we will only focus on this model and supersymmetric generalization of this one. And the reason is the topological recursion was first discovered and observed by solving this model. So it's a quite reasonable approach to start with this one and to think about supersymmetric generalization and try to find the recursion associated to such model. So this n by n one, it's kind of important, one Hermitian matrix model. So this comes with, of course, n, that's an, and also you have so-called strict complete constant, and dk, this is sometimes called kdv, kp times, sometimes called couplings, some sort of parameters. And I think, yes, so this is not quite defined as something like this. E to the minus gs of the trace of v to the m, not v to the m, sorry, e to the this, where v of x, well, in this case, of course, you put matrix in it and take a trace, but in general, v is defined by a power series whose coefficients are exactly this one. Okay, this is called the partition function of this. Okay, and then the reason I put this quotation is that you actually have to be careful about a whole bunch of things, because it's even very difficult to define, but you can. But if you just write this, this is not sufficient to uniquely define what model you are thinking of. Okay? Integral over hn. Yes, thank you. Any other typo? Not typo, but. All right, but okay, nevertheless, let's take this some sort of working physical definition. Okay, I mean, I'm going to define it later anyway. But okay, now we take dm to be un invariant measure. We take this to be un invariant measure. Meaning that any conjugation by un object would not change this measure. And of course, now your integrand is also taken by trace. So everything is invariant under un transformation. And then it turns out you can diagonalize by this un symmetry, this matrix. And then you can basically now rewrite this in terms of just integral with respect to eigenvalues. Was it mentioned? Yeah? Okay, it was in the first talk. Good. So then now, still I'm going to put this quotation. And then so now you have the whole bunch of this, and then Van de Mon minus GS So now because you have already diagonalized by this UN symmetry, what you can do is n v of lambda I. So now instead of having a trace, we have the sum of all eigenvalues on the exponent, where this is so-called Van der Waals factor. This. All right, so then now finally you can kind of try to make sense of this object. First of all, if this is a power series and integral, okay, so in principle, first of all, because this we studied as Hermitian matrix models, we diagonalize it. So now this is basically going to be a real number. Okay, eigenvalue is going to be a real number. So in principle, lambda I goes in R. Right? So then now you ask a question, what happens, because this is a power series. So what happens if the integral may blow up? So now what you can do is, okay, suppose you fix the degree of V, meaning that, okay, let's say this is in fact now the polynomial. Let's say we fix this V to be degree D. Okay, and then now you can kind of make a wish that this may converge, given that the highest degree part, the real part of the highest degree of this potential part, is the entire thing. If it's negative, then it dumps fast enough, and you make a wish that this is going to be convergent. Does that make sense? If you choose, and then if you choose the real part of, I think if I'm not wrong, GS over TD is, wait, no, but I have minus sign there. So if it's positive, and then it dumps fast enough, and also I probably have to assume that D has to be 2D, because otherwise the negative part is going to be blowing up. Or what we can do instead is that now, instead of saying that lambda should be R, we can say that actually it goes through some sort of path. Okay, so now we allow lambda to be in complex, but instead we take integral to be some path along, we integrate lambda along some specific path such that the integral will be convergent. That's another way of writing. Does it make sense? And in particular, we take this lambda to be the steepest descent of this potential. So you basically take the derivative of this and find out the zeros, and then this has to pass through at least one of those points. If you do that, then now this kind of makes sense. So basically the missing factor to define this object is basically the choice of this one. If you choose this in a nice way, then you can define this to be the proper matrix model thing. GS, T, now 0 to D, and it also depends on the path. Now this is something you can think of. We can try to compute something. Okay, so an important remark is that even though we started from these matrix models, what you end up with is just eigenvalue models. Okay, so sometimes this way of thinking is nicer if you think about some sort of countings. If you count some polygonulated maps of this Riemann surface in terms of this potential and blah, 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 that's actually useful, and you can actually do some sort of formal thing. But this one, if you actually want to think about conversion, then this should be something you should, this is something you should think about. All right, so this is kind of what we mean by matrix models, but okay, I just wanted to say that this can be defined, but again, we're gonna abuse some sort of notation, and now I'm gonna allow again, however, we still take this Vx to be again, the power series in X with infinite many. And this gives nice interpretation of the matrix models. Okay, so I just wanted to say that it can be defined if you do all the procedure, but still this way is kind of nicer if you want to generalize in terms of supersymmetric extension. All right, so now, yeah. Not necessarily. Yeah. And that, by the way, so that's a good question. So, okay, let's do the other one. So suppose I take this to be exactly the same for all of them. This, after taking so-called double scaling limit, you get genus 0 spectral curve. Okay, but if you choose, say, half of them to be that of one, and the other half should be is something different, and you actually find genus 1 spectral curve. And the information about this is basically equivalent as saying that you choose a filling fraction. Okay. No, I mean, you're talking about this? Yeah, but the fact that you have filling fraction or the fact that you have algebraic curve, it means that you have already chosen the degree of the potential. Right? So you are not doing formal thing. This one? Which one you're talking about? For V? Then yes, sometimes it works. For example, if you take this to be log as in, then you expand in X, so of course it's going to be power series in X, and then you can sometimes get the convergent ones. Okay, yeah, that's definitely true. So if you take the polynomial, then this, I can make sense of it, and if it's the convergent series, and you need extra careful prescription, that I actually don't know. All right, but okay, even though it can be defined, but to think about supersymmetric generalization, it's nicer to stick to this description. Or in other words, this is not uniquely defined, but you can still think of it as a formal object. All right, so now so if you take this description, what you can show is that, so out of blue, I'm going to define this operator by something like this. Not G. No, I think this is. Okay, now suppose I think this formal object, which is by no means unique, but what I can show is that then you can show that this is actually an exercise. You can show that that guy is 0. This is called the Virasoro constraint of matrix models, and I will now make a remark that this Virasoro operator is not the same as what Nitten said. I think you did KDV, right? Yeah. So this is different from the Virasoro operator that appeared in Nitten's lecture. They satisfy the same commutation relation, but the way it's written is slightly different. And this is going to be very important later. And the difference about this is also in the exercise sheet. That's in the exercise sheet. You have to do it. Yeah, right. I think everyone should do that exercise. This is actually a very important point. But anyway, so now out of blue, I introduce these differential operators. And then I just tell you that they satisfy this n plus m Virasoro subalgebra, because it just has -1. And then, by the way, you can show that if you think about this subalgebra, central charge never appears. The central element never appears. All right, so this is, from this perspective, this is a property that matrix model has. Now I want to take the other way around. Can we define matrix models by this condition? And the answer is yes. So, with some property, but the answer is yes. So now that's basically an idea. So now I'm going to take, the idea is, can we define matrix models from Virasoro constraint? If we can do that, so the reason why I want to do it is because now it's easier to generalize into supersymmetry. So now I'm going to say tilde. This is, I'm going to take almost the same form, delta tilde lambda and e to the minus gs trace, sorry, not the trace, sum. And v lambda I. Okay, again, this is just the formal object where this delta tilde is now, at the moment, unfixed. Okay, so it's the arbitrary object. So this is my definition of the tilde. Okay, this is just a formal object with some unknown integrand. Now I ask, what is any condition such so? Then now I impose, to prepare this. So the step 1, you just think about this formal object. Step 2, you impose this condition. Okay. And then you ask a question, can you uniquely fix this one? And the answer is, by assuming some condition, which is written in the exercise sheet. It basically means assuming that integral by part doesn't give any contribution. Assuming that, you can show that up to overall constant, this is in fact. So then you can show or prove that up to overall constant, this lambda is in fact this one. Is the concept clear? So okay, I prepared this object. So the purpose is I want to define matrix. How I present it so far is that this is a property of matrix models. I had some other definition, and I derived this. I want to take the other way around. I want to take this as a defining property of the model I'm thinking of. And then to do that, of course, if you just ask highest weight vector, it's just a random thing. So I have to give some condition such that the solution is going to be unique. And also such that the solution is the same as matrix models. And then the condition you have to impose is that if you think about this form, but only this part is unfixed, and then this is sufficient to fix the Van der Monde part. Yeah?
And you consider the freedom?
No, power series. It has to be just power series in this T. V has to be just arbitrary power series. So this has to be this. And the reason why is because I'm taking these differential operators with respect to all T's. So I have to keep V to be a power series with these specific coefficients. This Tk is exactly the same as this Tk. Okay, then you act on it and you have some integrate by parts, and assuming that there's no contribution from the boundary, you find this up to overall constant. Does that make sense? All right, good. So now I think, can you guess how you can make this supersymmetric? I guess kinda, right? Now I think, at least I hope conceptually clear what you have to do to define super eigenvalue models. All right, so now what we've studied so far is that we can actually define matrix models from the Virasoro constraint of some specific representation. This is important again, but now we want to, because this model is purely defined in terms of Virasoro operators, we can try to generalize in terms of super Virasoro operator. All right, and then now, and also it's important, so matrix models just turn out to be eigenvalue models. And eigenvalue models have a nice thing in terms of this Virasoro constraint. So from eigenvalue models to, we now want to think about super eigenvalue models. So how do we do that? So, okay, I don't think there's any definition of super eigenvalue models themselves, but we can define the partition function of super eigenvalue model in a similar way. So let's say super, okay. So, okay, basically we want to impose a condition very similar to this. And there's actually some reason or some motivation behind why I'm gonna set this specific form, but for now you can just take it as a definition. I goes to 2n. I'm gonna explain why this is 2n. 2n of the theta I, where lambdas are even coordinates, like the eigenvalues that we have seen so far, and thetas are odd coordinates or odd variables. So they're anti-symmetric. And I impose the same condition. So now, of course, this can depend now on not only lambda, but also theta, odd variables. And now I take the same expression, and I have sum to n. So this is exactly the same, right? But now I add such that, so Vx is the same as last time, just a power series in this even parameters. You have to be careful that the variable of integration is lambda, but these parameters are floating around. And these are the parameters that you act Virasoro constraints on. And what is this guy? The psi of lambda, or x maybe. This is, just for notational reason, we have k plus half xk, where k is. And now, theta, as I said, this is odd. This is odd. And I want to take the entire thing to be even. So to make it even, we have to impose that this. So basically, a partner of these parameters, this should also be odd, so that the entire thing, this thing is going to be now even again. Okay, so now it makes sense to take exponent, and then, so this is basically an ansatz of my partition function. Okay, so this is called the partition function of super eigenvalue model. Okay, so far it's just a symbol. But now, remember, basically, we want to impose this condition. And the question is, can we uniquely fix this thing? If you can, then it's a supersymmetric generalization of matrix model. Maybe not the, but still a plausible candidate to study recursion. All right, so then now, the important element is what is this and what is G. So now Ln and G are for n. This is Here you go. 3.6 in 18, and then this is 3.7. And then I don't think you want to write down on your notes, to be honest. It's very messy, but there's a canonical construction to write down the differential operators. And you can actually check that imposing the super Virasoro constraint, it actually uniquely defines this imposing GRZ equals 0 for r greater than half minus half. This uniquely fixes this to be yep.
Are they independent reference of variables, or rather like the internal of the check size are actually t-test, and also one has half integer and this is integer ones.
Okay, so the first question, the theta and x's, they're independent. The thetas are the odd variable that you integrate, and the x's actually remains. Formally, this depends on x's. Okay, and then also these Virasoro operators, they are differential operators with respect to t's and x's. Okay, that's the answer to the first question. And the second question?
Second question is also simple.
Okay, good. I think you're talking about half, and but this is more like a notational thing. Yeah. BPS, no. No, it's a very good question actually. It's a super good question, and it's a typical question from physicists. The answer is no, because this is n equal 1. Is that satisfactory? Okay. Yeah, but yeah, yeah, you have to think n equal 2 in this case. But if it's n equal 2, I actually have some idea, maybe something. But is there any comment I should do? Yeah.
If you have, why do you only have linear terms in theta?
This?
Yeah.
Okay. Good question. Yeah. So what is? So as I said, okay. So the question is why I even put the answers in this specific form, right? And then this is coming from VOA in some sense. So you know the exponent of, suppose this is the free boson of physics. So it's the integral of the free boson that Ranier defined. So this is actually integral of the J that Ranier defined. So this basically appears here. This is an exercise, by the way. If you have something like this, so suppose I introduce Z1 to be, okay, suppose I think about something like this kind of operator, integral of Ranier's normal order. Okay, and then now you take this, and you think about normal ordering of this operator, you actually find exactly the Van der Waals of, okay, this is another way of finding bosonic Van der Waals. Now, a natural supersymmetric generalization is you add this. So this is a natural supersymmetric generalization. But this is kind of why I said it's not the, but so you could have tried to add some stuff here.
But I mean, you added more stuff, right? Like in the bosonic variables, you added like all powers of x.
Yeah, that has to.
Yeah, but no, but you can.
No, I know. No, that's what I'm saying. This is just a natural, the simplest. Maybe this is a simple supersymmetric generalization. and you can try to have a little more complicated thing. But at least one motivation is this is just a natural object to study from safety point of view, at least one simple, well-behaving object. And if you think about the product, and then I don't know any models having that structure, but at the same time, I don't think it's impossible. It's just difficult to see what kind of, I don't even know if it's going to be super symmetric in the sense of Virasoro constraint, but could be. Yeah.
Why do you have an even number of eigenvectors and super?
Ah, good. So it's, okay, this is also kind of an ansatz, but from this perspective, you actually get the same number because this, if this is your starting point, and you have z and theta, they always appear as a pair. If you have the product of those, you get the same number of even and odd variables. But if it's 2n because we want to have this part to be even. This is again ansatz, but it's a reasonable assumption that because this part is even from this construction, we assume this part is also, we want it to be even, then you have to have even number of integrals. But of course, if you try to generalize by say odd number of things, and this would be odd Van de Mon, and such model might exist. I just don't know. So it's like a canonical or as simple generalization. And then maybe just last comment because already 10 minutes after 10 minutes past 1. Here I impose only G. I didn't impose L. Why is it okay? Why is it a problem? Can you say something? Yes. All right. So it's actually, so imposing this condition is sufficient to say that this is also 0. So this implies that for n greater than -1. All right. So I think I'm going to stop now, but basically, I hope the idea was clear. So we start from Virasoro, so matrix model was defined in terms of Virasoro constraint, and we take that as a defining property of matrix models. Now we generalize this Virasoro constraint to super Virasoro, and we found a model. Not necessarily the best model possibly, but we find a model. So what we can do is we can study a recursive structure of this guy, which I'm not going to present because now I want to make it more like abstract approach. But at least now you have in mind what kind of model you can think of from the algebraic approach that we're going to talk tomorrow. All right, so thank you for listening. Yeah, okay, so yeah.
What space is it? The land is a real number.
Sorry, which one?
The theta, the odd, this new odd variable. Is it like, is it living from space?
Well, you could give some sort of meaning, but I think, at least for this case, you can think of it as a formal object. And in particular, for the integral, you don't have any geometric meaning. It's more like a sign. But yes, you can give some geometric meaning. And yeah. Yeah, right. But yes, yeah, you're right. At least that's sufficient to think about this model and even tomorrow's lecture too.
Related to that, since there are mathematics, can't you just compute the data intervals? Can't you just compute the data intervals? Like expand the exponential data?
Yeah, you could, yeah. Okay. Oh, okay. If your question is can you compute it explicitly, then I don't think you can always do that. Because remember, even for matrix models, this is still the formal object, right? And we have to specify what is the, so this one, you can just think of it as formal integral. But for this one, you actually have to specify the data. So specifying that data, and then in principle, you can do an integral.
Can't you just integrate out the data?
So theoretically, yes. And there's actually some formula for this model. Okay, so the answer is yes for this specific model, because there's some nice, very, very non-trivial simplification happens. And you can actually show that, I can't remember at the moment, but roughly speaking, if you take a log of partition function of Hermitian matrix model of size n, this would be, okay, might of super eigenvalue model of 2n. No, I think 2n is here, and such that if all epsilons are 0, modulo some parameter that I don't remember. But this is very special example. And if you actually think about, so they were like in the NS sector. If you think of Ramon sector, that doesn't happen anymore. Yeah.
If you consider more generic potential in your exponential, and I don't know if you did this computation, but don't you have in your, okay, let's say you have generalized underneath this correction, so new contribution?
Sorry, you think if you modify this part?
Yeah, you have theta I, theta j.
Yeah. Then of course, right? Yeah, you could that. Okay, I'm not sure if it's still going to be annihilated by the same Virasoro operators, but it could.
Not the same Virasoro constraint, but I was speaking about the delta t. You will have some modified circuit.
This one?
No, yellow, not mono.
Yeah, but I thought the. Sorry, say that again.
Consider theta I, theta j.
Yeah.
You have delta t of more generic expression. I would expect something. At the end, if you consider exponential minus log of delta t, it will not compensate, but
Okay, I think yeah. Okay, yeah. Maybe, but yeah. As I said, I wouldn't rule that out. It might be possible that you might be able to add more stuff here and then modify the measure and also possibly the Virasoro operators. That might be totally possible. I just simply don't know if such things is even possible.
My intuition is telling me that the number one shouldn't change. Because it's number I minus number j and it's I to j is very natural.
Yeah.
Can you explain why the random one's not squared?
Why there's no square here? It's a good question. It's a very, very good question. And then I think the best answer I can give you is this is what it is. Okay, of course I can do a little more justification. Okay, suppose you turn off all these x's at this level, but a priori it's not clear at all that this corresponds to the standard matrix models, because you have thetas here, and remember that integral of d theta itself is 0. So you have to have correct number of theta coming from this Van der Waals, and then the leftover would be something. And then it turns out, as I said here, there's a relation if you turn off all variables to have. So basically, if you have square here, you have extra factor after you integrate over the theta. So it's more like I'm talking from the consequence, but that at least justifies that if you start without square and then integrate all thetas, cut off all, turn off all of them, and then it in fact the square appears. So yeah.
you say anything about the representations of the superly algebra from the matrix model? Can you say anything about the representations of this super algebra from the matrix model? Is that good?
Sorry, I don't think I understood your question right.
Right. I have a super algebra.
Yep.
I have representations associated.
Yep.
Now I show its dual to this wonderful little partition function that gets annihilated.
Yep.
What can I say about those representations from this?
I don't know. This is basically the highest weight vector of your module. This is the highest weight vector of your module. Yeah. But then now if you think about literally if your Fock space is as Barnier showed, it's just power series thing, and then this is exactly the highest weight vector of the Verma module. It's not the yeah.
Here, these arithmetic models, but in principle, you can also consider matrix models with external fields.
So, okay, so are you talking about conservative matrix model? Okay, good. I would expect yes, but what you have to be careful about is, in principle, this matrix model, or even without super, is not the same matrix model as conservative matrix models. Yeah, so, okay, in principle, you can take so-called double scaling limit, and then the partition function, in fact, coincides with the conservative matrix model partition function with some proper dictionary. So you can ask the same question. If you take those so-called double scaling limit, what happens to this case? And that, in fact, is going to be exactly the supersymmetric analog of the conservative return type thing. But that's more like, you can actually show that from VOA point of view. Is that okay? Yeah.
Why is right by something like a Jacobian?
Jacobian? Is that what I said?
I guess in that sort of situation.
Yeah. Van der Mon, yeah.
When you integrate it.
It's not Jacobian, but okay, what was the name? Okay. I think. Okay, maybe we can talk later. Yeah. Sorry. Any other questions? Good. Sorry, what? Good question. So there's no notion of triangulation anymore in this super eigenvalue case. Is that your question? So matrix models can be thought of as polygonulation of Riemann surfaces, then you can actually count maps. Are you talking about the super analog of that? Yeah? Sure.
We have a picture of what a matrix would look like that has this as a spectrum.
Then I think the answer is no at the moment. Right, so this is actually not the same as super matrix models. You can do that. You can actually, you have a matrix and you can honestly generalize matrix to super matrix and taking super trace, and then you can think about that model, and it turns out this model is trivial. Yeah, if you integrate, if you cut off all the fermionic part of these super matrix models, it gets, I think, okay, it's exactly the same as basically the standard matrix models. But this one gives additional ones because it's, okay, in this case, okay, it's a special case, so this has a relation between the matrix models, but they have additional one.
That's Kento Osuga.
Yeah.